Hi, everyone. So today we're going to talk about Newton's second and third laws. So Newton's second law of motion review. First, let's go over what is Newton's second law. So if you ask a physicist, what is Newton's second law of motion, they would tell you that it is F equals ma, right? Now, when Newton first described it, he described it in terms like the acceleration of an object can be determined by the force acting on the object divided by the mass of the object, things like that. But we usually use it as an equation, F equals ma. You can also use it as the equation F divided by m equals a, or F divided by a equals m. Those are also acceptable forms of the equation, but usually we just stick with F equals ma. Now, what we want to do is, number one, we want to write the second law for each of the following components. For the sum of forces in the x direction, sum of forces in the y direction, sum of forces in the z direction. And we're going to do that because we will have free body diagrams, FBDs, in multiple dimensions, in possibly in 3 dimensions. So we want to be able to know, what do we do? How do we split that, right? How do we split it into x, y, and z? So first, summation of forces in the x, you have F equals ma, right? Sum of forces equals the mass times the total acceleration. But now we're splitting it just in the x direction. Well, mass is a scalar. It doesn't have a vector, so it can't go in a direction, right? But acceleration is a vector, so that would be sum of forces in the x equals max, and in the y you have may, and for the z you have maz. So we can split this into 3 accelerations, and then we could Pythagorean theorem to find the total acceleration if we needed to. Now, the second law helps us connect with a concept that we have talked about a lot in this course so far. The force is now connected with acceleration. Acceleration has been the cornerstone of what we've talked about so far. Our physics has surrounded the idea of constant acceleration up to this point, right? We did some calculus with non-constant acceleration, but the physics equations that we use, the orange equations or the general kinematic equations, are for the most part constant acceleration, right? That's what we have to have in order to do the math. And same for Newton's laws, right? Newton's laws are going to yield a constant acceleration. Now, if that acceleration is moving, you've got to involve calculus with Newton's laws, and that gets complicated, which, buckle your seatbelt. But we won't work with that quite yet. So the second law helps us connect force with this common idea of acceleration that we've had so far. Number 3, show mass is different than weight. So weight can be shown as that. It's the weight force, right? Weight, or you can write that as the force of gravity. That's how I usually write it on my free body diagrams. You would write that as mass times gravity, right? The mass of the object times 9.81 meters per second squared. So this is how weight is different from mass. If you, for example, we have this picture of an astronaut. This astronaut, if he had the same mass, or she had the same mass on Earth as they do on the moon, the mass wouldn't change, but the weight would change, right? So your weight is completely dependent on the gravitational field that you are experiencing. It relies on that. If you have a different gravitational field, that's going to give you a different weight. Now, your mass can obviously change. It varies throughout the day depending on what you eat, how much you eat. That can cause your mass to fluctuate throughout the day. But in general, your mass stays the same, give or take a kilogram here or there. but the weight can drastically change if you change the gravitational field. It also asks us to write using scientific notation, or scientific, SI units. So the unit for weight, or F of G, is newtons. The unit for mass is kilograms, and the unit for gravity is meters per second squared. So mass is in kilograms, weight is in newtons. You could also say weight is in pounds if we used empirical units, and that would also be over here. Pounds does not measure mass. So this also shows us that a newton is a kilogram meter per second squared. So that's writing using the SI units. Now, as a rocket is fired from rest, its speed and acceleration increase with time, even though the force provided by the engines remains constant. Why? So this is common in space travel, right? We have, whoops, let me bold that. Force is constant. It starts from rest, and it continues to accelerate. So acceleration is not constant. It continues to accelerate and increase its speed with time. So if we look at this from F equals ma, right? Flip my iPad. So if we look at this from an F equals ma perspective, acceleration is increasing, right? So you would expect that the force would also need to be increasing in order to push the acceleration harder, right? But that's not the case. We are told that force is constant. So if that force is constant, that means only one thing. To balance this out, mass must be decreasing. And this happens with rockets all the time, right? As they use that fuel to create the force of thrust to cause that acceleration, that fuel is being depleted quickly, and that causes a decrease in mass of the system. So you have a constant force, and the acceleration may continue to increase as the mass starts to decrease. And that increase of acceleration will be proportional to the decrease of mass. So we can look at the F equals ma relationship there in that way. And that's not an uncommon example either, or an uncommon scenario where acceleration must increase, so mass must decrease, or if mass is increasing, the acceleration will start to decrease. All right, so that was it for the second law. Let's go to Newton's third law. So Newton's third law, before we start, okay, Newton's third law is that for every action, there is an equal and opposite reaction. Oops, so I'm gonna write that real quick. Maybe I am. So for every action, there is an equal but opposite reaction. And that might be kind of confusing, right? So if we have this idea that it is equal but also opposite, what does that really mean? Well, we have to look at this in a vector format, right? So vectors, a vector has magnitude, right? So something could be equal in magnitude but opposite in direction. Or something could be equal in direction but opposite in magnitude, which is not the case for this law. But vectors are equal in magnitude but opposite in direction when we look at Newton's third law. So let's look at this image over here. We have these two objects exerting a force on each other. It looks like it's just a general gravitational force. But we have the force that 2 is putting on 1. We have the force that 1 is putting on 2. And if we look at them, they are equal, right? With this tiny exception they are going to be opposite in direction. Okay, this is the case for any force interaction where two objects are interacting with each other, no matter how big or small the object. If we look at tiny particles of gas or something like that, those can sometimes have exceptions to their rules, but small and large forces, small and large bodies, all would operate with these rules. Now, Newton's laws don't always apply perfectly to atomic and subatomic level, but Newton's laws usually apply very well on the macroscopic scale. So let's look at some examples for Newton's third law. If a fly collides with the windshield of a moving car. Okay. First, letter A, which experiences the greater force? Right. So we've got a fly colliding with a windshield of a moving car. So we have the force of the windshield on the fly, right? Now that will equal the same force but opposite direction force that the fly exerts on the window, right? So which experiences the greater force? Well, if we look at this, they are equal, right? So that is the same force as this one. You just have opposite in direction. So they experience the same force, the fly and the windshield. Now, one of them is going to feel it a lot more than the other, right? Your windshield does not get cracks and dings every time a fly runs into it, but those flies definitely feel your windshield as they splat on your windshield. So let's look at that part B, which experiences the greater acceleration. So let's write out the second law, F equals ma, right? A force equals the mass times the acceleration. Now, if let's say we're comparing two force pairs, right? And we want the force to remain constant. We talked about this before. If the force is constant, the mass and the acceleration can fluctuate proportionally. So we have a very large mass on the windshield, very small mass on the fly. That means that the windshield will experience proportionally very small acceleration, and the fly will experience a proportionally very large acceleration. So this force, again, is the same force for both objects, but the one with the large mass experiences small acceleration. The one with small mass experiences large acceleration. And in this case, that acceleration exceeds the integrity of the object, and the object breaks. In this case, it's a fly splatting on a windshield, but the fly breaks under that acceleration, under that force. Okay, number 2, if a block is sitting on a table, is there an action-reaction pair of forces we can describe? So here is an action-reaction pair that we talked about, right, with the fly and the windshield. Here is your action. The windshield exerts a force on the fly. Then the fly reacts by exerting the same force, right? And that can be flipped vice versa. Now, we have a block on a table. That is block, okay? And it's sitting still, sitting on a table. But we know that there is the force of gravity on that block. So what is the action-reaction here? Well, gravity is pushing it's pulling the block down onto the table, right? But the block is not falling. The table is resisting that. So the table pushes back with an equal force called the normal force. If the normal force is a little confusing because the name doesn't really tell you a whole lot about it, you can also call this a contact force. If you're in contact with any object, there is a contact force, right? There is normal force. If you lean on a wall, if you sit in a chair, if you have a block sitting on a table, if you're in contact with something and you're leaning on it or sitting on it with any kind of force, with any kind of weight, then it is pushing back on you. unless the integrity fails and the table, chair, wall, whatever breaks, right? Then there's new scenarios for that. Now, normal force is going to accommodate whatever force of gravity that it's going to feel, or whatever force it feels in general. Let's say we have a big block A, we have a medium block B, and we have a small block C. Mass of A is greater than mass of B, which is greater than mass of C. Okay. Now, if we were to look at the normal force for each of these, right? The normal force for A has to balance the weight of the block, assuming the table is not breaking. So assuming the table doesn't break, the normal force on A is going to be much stronger than the normal force on B, which is stronger than the normal force on C. So normal force is this variable force. It will match whatever it needs to match as long as it doesn't break, right? So for this table, as long as the blocks don't break the table is going to match it pound for pound or Newton for Newton. Same for a chair. If you're sitting in a chair, if we say we have 4 different students sitting in a classroom, they all are going to weigh it differently, but the normal force is not going to be the same for each person either. The normal force will match their weight to keep that chair from just sinking into the ground, from the chair breaking, from them plummeting to the center of the earth, so on and so forth. So normal force can actually vary to match whatever it needs to until it breaks. Okay, so that's kind of how Newton's third law is going to work. If an action is done on an object, say a fly hits a windshield, the windshield hits the fly back. The same for gravity, as we showed over here. You will have the same gravitational pull by 2 objects, but you also have to remember that if you are pulling really hard on a big object, it's going to feel a small acceleration. And if you're pulling really hard on a small object, you will have a big acceleration. That is why our gravitational pull does not really affect planet Earth all that much. A lot of mass, not a lot of acceleration. All right, this is Joe Dirt's meteor. Okay, we've got a 747 that drops a load, right? The frozen bits of pee and poo. Frozen into a sphere or a round object mid-flight. Okay, explain how the motion of the frozen mass, that looks more like a fish than a plane, but you know, whatever. Explain the motion of the frozen mass, explain how the motion of the frozen mass can be described using each of Newton's laws of motion. Which do we use the most in our problems? So Newton's first law, an object at rest will stay at rest, an object in motion will stay at motion unless acted upon by an outside force. So we've got this plane and it drops the load, right? Now it's going to continue because it has this horizontal velocity, but it's going to have this arc to it, right? This can be shown, and we can describe this under the first law by saying that mg, or the force of gravity, will change the motion of the object, right? You can also say that air drag is changing the motion of the object. So there will actually, in this scenario, you would say that there is actually an acceleration in the x direction if we're not including air drag, and there is acceleration in the y direction caused by gravity. So that's how we can look at that from first law. Now, from the second law point of view, we can start analyzing the forces that are causing this mass to accelerate. So if we get a diagram here, we can just call it a point. Okay, we have a down force, F of G. Put your vector hat on that. Then you have the air drag vector right there. So now we can see that there is going to be an overall acceleration down to the right. And if we put that up here, what do you know? Now it looks kind of like the arc of circular motion, right? So that holds up. Looks like that object is going in an arc because of this angled acceleration. So we can see with F equals ma with a free body diagram or an FBD that the unbalanced forces down and to the right are going to cause that arc to happen. Then with Newton's third law, for every action, there's an equal and opposite reaction. So this one's going to be a little different. Let me see if I can get a better plane. Okay, so as this plane drops this mass, it technically is so you can analyze it as it's pushing down, which will cause the load to push up on the aircraft. That can also be looked at a conservation of mass in the system rule. You can also look at this in space. If you're traveling in one direction and you want to slow down, you can throw an object out and it'll push you backwards because of conservation of momentum, right? So this can be analyzed for Newton's third law. There is the force of the plane pushing the turd out, and then the turd would push the plane up ever so slightly. And remember, we've got the ratio of mass to acceleration to think about there. So the plane's probably not going to move a whole lot unless there's a whole lot of poop. Now, there is also the relationship where the turd is pulled downward, right? Let's just erase that altogether. The turd is pulled down, and then the Earth is ever so slightly pulled up, right? Because we have force due to gravity, and here we have force due to turd. You also have a third law pair there, an action-reaction pair. You can also look at the action-reaction pair of air drag, but that's very rarely done, that you look at the force that you are exerting yourself on air. So that's not really something that we look into very often. But those are the three ways that we can look at this using Newton's third law. Okay, now our last slide. This is information taken from Mr. Askey's duck walk. His duck walk is used to analyze the second law of motion with Newton's laws, right? So we have this graph, force versus acceleration. So let's graph this, okay? We will put force in the y-axis and acceleration in the x. Now I'm forcing that so that we can get the right result that we want. So force goes up to 30, right? So we've got 30, 20, whoops, that's not going to work. Miscounted. Let's start here, 10, 20, 30, 40, right? Then our acceleration goes up to 4.5. Let's say that this is 1.5, 3.0, 4.5, and so on. Now, let's graph it. At 0.8, so about halfway to 1.5, we also have almost halfway to 10, so let's put that dot right there, about halfway in the middle. At 1.5, our meters per second squared, our force is 10. At 3 meters per second squared, our force is 20. And at 4.5 meters per second squared, our force is 30. Now, if we draw this line, we can see that that is a linear graph, right? And we can actually look at that and analyze it. So number one, we graph the force versus acceleration. Now let's determine the value of the slope. Slope is rise over run. So we have 30, right? It goes from 0 to 30. And it goes from 0 to 4.5 on the bottom. So if we have 30 divided by 4.5, let me do that math right quick. 6.66 repeating, say 6.67. Okay. Now, what does that slope mean, right? Number 3, what does that slope even represent? Well, if we look at the units, right, we have a Newton divided by a meter per second squared. Let's break that down. A Newton is a kilogram times meters divided by second squared. And we're dividing by meters per second squared. Let's multiply by the reciprocal, right? That would be seconds squared divided by meters. So the seconds squared cancel, the meters cancel. That gives us kilograms, which means that the slope of this graph gives us mass, right? And if we look at this, F equals ma, well, if we divide that a from both sides, you get F divided by a equals m. So that is just a way to prove Newton's second law with real data, right? This is real data that we got from an experiment. Granted, you guys didn't get to do the experiment, virtual and all, but this is a way that we can show support for Newton's laws of motion. All right, next time we will do a few more example problems with Newton's laws of motion and continue on through chapter 5.